analysis and interpretation of the metric data. So, this is also a reminder from the last talk. I was talking about the cosmic rays, and that when they arrive at Earth, they interact with the atmosphere, with the molecules in the atmosphere, and they produce showers, cascades with many, many secondary particles. And the interesting fact for us now is that the gamma rays produce a very symmetric shower because of only electromagnetic interactions, whereas the protons make much more scattered shower with much more transverse momentum, and also different components, muon components, hadronic components, and electromagnetic components. So we are using that now to distinguish between the gamma rays and the protons, because the gamma rays are 1,000 times less numerous, so we have to suppress the proton background severely. I said Cherenkov astronomy. What does it mean, Cherenkov light? So something very interesting is happening when these particles arrive at Earth. They are so ultra-relativistic that their speed is really, really close to the light speed in vacuum. So when they hit the atmosphere, they are faster than the allowed speed of light. The allowed speed of light in the medium. Allowed speed of light in this medium. So they have to be slowed down. How does this happen? It happens because, in principle, these particles excite, the charged particles excite the atmosphere molecules, and they all create Huygens waves. I don't know if you're familiar with this very simple Huygens primary wave principle. And normally when you have a particle that travels with light speed, all these waves can annihilate each other and you get a net effect of zero. But since the particle is moving faster than the speed of light, these, here you see these as concentric circles, these waves cannot annihilate, and you get a net positive effect, which is like a cone in the direction of the particle. And this is very similar to the supersonic shock wave you get from an airplane when it crosses the sound barrier. And we can see the effect very nicely in atomic reactors. I see it here. Because the same thing is happening. Relativistic particles are produced, and this time we are talking about water as the medium, and water, the light speed is of course even more reduced, so you see the effect very nicely. What you can see here also very well is that the light is blue, and what you cannot see is also mainly ultraviolet. So we have these showers in the atmosphere, and they create the Cherenkov light, and the cone is very small, only 1 degree opening angle. So you have the showers mainly, or the maximum of the showers at 8 kilometers height, and at the ground this means you have a light cone of 120 meters. So you put the telescope within this light cone, and then you can detect, if you are sensitive enough, these flashes. But it's very important, what I didn't mention yet, we are talking about ultra-relativistic particles, and also all these secondaries have a lot of kinetic energy until the shower finally dies out. So the whole thing happens within nanosecond time scale. So it's very fast. So we cannot use the standard CCD camera from an optical telescope. We have a very special PMT camera, which is sensitive on the nanosecond time scale, and we see very short light flashes in our camera, which we then reconstruct to images, and I will show you how. The new thing that is now being done is that you use not only one telescope, as it was originally only the Magic 1 telescope on La Palma, but now we have 2, which means simply that you are reconstructing three-dimensionally this shower. You see it from different angles. You are able to reconstruct the height and the distance of the shower, because if you have only one telescope, you can have some kind of Fata Morgana effect that you don't, since you don't know the actual size of the shower, because it can be different depending on energy and distance and so on. You need 2 telescopes in order to precisely reconstruct energy and distance. The energy range we can cover with these goes typically from 25 GeV. This is especially magic with a special trigger for low energies. Other telescopes are higher, 100, 150 GeV, up to 100 of GeV. So we cover a very large range and also a very high range. And, well, this is very important because the satellite experiments can go up to, let's say, 300 GeV, but with very limited statistics because the volume of the Fermi-Lat, well, is something like this size. Whereas we have an effective area, as you can see here, of something like 10 to the 4, even 10 to the 5 square meters. So it's orders of magnitude larger, and we get much, much better statistics. But satellites like the Fermi-Lat, they don't have the background problem because they can make a veto for the charge of the protons and electrons and so on, which we cannot. We do not measure charge. We measure only the CHERENKOV light that these secondary particles produce. So we have a severe background problem here. So here I'm drawing the light density from the CHERENKOV light on the ground. So for the gamma ray, you get, as I said, this cone around 120 meters or so. Very symmetric, very nice. For the proton, you're getting these sub-showers, this structure, which means that you get some light here, some light here. So typically, we are able to differentiate between them because the images that we see are much less symmetric for protons. But it can also happen that you have maybe your telescope only here, and you see only part of this whole shower, and the other part is hidden for you because it's too far away. And then it may happen that the proton looks very much like a gamma ray. So, yes. Well, these additional hadronic interactions that are possible to produce positive, negative pions, kaons, and so on, they can have larger transverse momentum than the electromagnetic. In the electromagnetic case, everything goes in the forward direction, whereas in the other one goes also sideways. Well, and then it depends strongly on how much the first or the second particle got, and then something goes this way, and that's the reason. Something. But you also have pi zeros, and they, when they decay, make a nice electromagnetic shower, so it can look very much like a gamma. And also, as I showed the other time, there's a bump in the electron spectrum, so there are quite a lot of electrons, also cosmic electrons, and they also produce a lot of background first. So this is one event as we measure it with metric. So this is the metric on camera. Here we don't have so many pixels. We have in this case 576 pixels. The new camera for metric 2 and the planned upgrade for metric 1 has 1000 pixels because there will be more smaller pixels here on the outer edge. It's simply an amount of money. Each of these PMPs costs more than 1,000 euros. I mean, they are very, very expensive. And also, all the readout at the end is very expensive. So the more pixels you have, easily doubles and triples the cost. Okay, what do we see here? Here we have the time, the nanoseconds. So this is a movie in half nanosecond steps. You can see how the shower is evolving. We have two different scales. The right scale is a bit higher than the left scale is a bit higher than the right one. So that here you can see also some noise, which is in that case not necessarily hadronic noise, but it's also night sky background noise, because also the night sky background that we have all around is a noise for us at a certain level, and you see these fluctuations that we see in the night sky background. It's not entirely completely stable. And well, what you see nicely is that the shower evolves over time. It goes in a certain direction, and this is also measured somehow for the distance that you see, but it's actually very complex. I was working on that for a couple of times when I was in Barcelona, because depending on the angle under which you see the shower and the distance, because part of the track is faster than the light, the speed of light in the medium, and so the shower is evolving faster than the light that is coming to you from it. So you have to be careful under which angle you see it, because depending on that you see the top or the end of the shower. So yeah, this is another thing. We follow the sources over the sky. So because in principle the gamma rays, since they are coming from the sources, if you would look up, basically you would see them coming from the same point in the sky. So Yeah, but we try to point mainly to zenith, because the further we go to the horizon, the more night sky background we see from the cities and so on. And also, the more volume we have in the atmosphere, and the more of this Cherenkov light is absorbed. So, and scattered. So, there are 2 points. One point is that you lose the lowest energy events because the light is absorbed and you don't see them anymore. On the other hand, you increase your volume even more, and then you can have more statistics for the highest energy events, simply because you cover a really large volume. Okay, another event. Let me see. So this is how it looks like. So an important feature of magic is that we reach really the lowest energy threshold of all the existing installations, which is around 25 to 50 GeV, depending on the trigger and other things. And this allows us, as I said, to make really the connection coming from the satellite in space down to the next energy range here on Earth. And this is very important because we are a pointed experiment. Fermilux is scanning the entire sky continuously, and they collect data and they integrate over time. But our camera has only a field of view of 3.5 degrees, so we really need to look. And then it is very helpful to get these catalogs from the Fermilux, and then we can point directly to these positions. So this is again the same camera and this image, now in a bit different color scale. The point is, what are we doing to differentiate the background from the signals we are interested in? We are parameterizing this image as an ellipse, and then we calculate the major and minor axes, and also some other things like angles, distance to the camera center, and so on. And since the proton showers are usually more fractioned and are spread more out in the camera, the widths especially will be larger, and this is the main possibility. And the other thing is that, as you've seen in the movies, that there's also time development along this axis, and that's the time gradient, and we are also using this. The most important source for us is the Crab Nebula, which is a supernova remnant now 1,000 years old, has been studied so extensively in infrared, radio, optical, X-ray. Why is it so important? It was the first source discovered 21 years ago, and it is the brightest persistent source in very high energy gamma rays in the sky. So it is the calibration source for all the experiments. Everybody that has a new telescope first looks at the Crab. It can also be seen from the southern sides, so it's also a coarse calibration source. Very nice, very important for us. Only problem is that we don't see it as the others. I mean, as you see it in optical or in X-ray, we see it as a blob of this circular radius here, and then these are like, this is the center of these different energy ranges, let's say. But what I'm trying to say is that our angular resolution is such that we don't see it as a structure, we see it as one point. And this is important to keep in mind for other results. But what we can do, and what we can do very well, is we can make a nice spectra on this energy range, what I was talking about, from 50 to even up to 100 TeV. And, well, as you can see, they connect very well to the Fermi satellite, which is red, and also previous measurements, and here, old measurements, I think, from Comte. So, that is working very well. Just to let me explain that this part of the spectrum is synchrotron emission from the electrons in the magnetic field in the Parseval Nebula, and then this is inverse Compton scattering, where the synchrotron photons are scattered to higher energies by interacting with the electrons from the nebula. Now, important point is we cover the highest energies well because of the large area, but we are background dominated, whereas the satellites are dominated by statistics because of small area. Now, recently, very strongly discussed also at the Texas Symposium where I was last week, is the question if it is really a standard candle or not, because data suggests that at least for the satellites it's not stable anymore. It was found in X-rays that the flux is decreasing over several years and the range of 10%. And also in gamma rays it was found that there were two clear flaring episodes Another one finally was reported from 2007. And there are claims from the ARGO experiment. I will not go into detail what ARGO is, but they are sensitive in the TeV gamma ray range also, that they see this flare during September 2010. However, they do not see this flare in February or earlier periods, so it's a bit fishy, and the significance they have is not really large, so they still need to work on that. But at the same time, MAGIC was observing, and also Veritas in the US was observing, which is also a CHERENKOV telescope, and both of us didn't see any change in the crab. So we were quite confident that, at least at the moment for us, it is still standard candle. This is an important point because many of the results that we publish are given in percentage of the flux of the Crab nebula above the given energy. And if this flux changes, then it has no meaning anymore. There are several theories of what is happening. This is a Hubble Space Telescope image of the Crab just after the flare. And you see that very close to the pulsar is here, by the way. Very close to it, there are these so-called wisps. There are features in this pulsar wing. There are even some jets that are not so easy to see here now. And the theory is that because the flare was very short in time, only a few days or so it cannot be the entire nebula that is changing. For the X-ray flux, maybe because it goes over years and can be a larger area, but the short time flux variability suggests that either it's very close to the pulsar, and you may just be able to see that here there's another second very bright spot near the pulsar that could be responsible for it. It is known that there are certain denser features in this pulsar wind that are also very bright, and that they are changing also the brightness. And this may be a reason, or maybe these other structures. Okay, I was talking about the pulsar wind detected in the CHERENKOV telescopes, but also the pulsar itself, the pulsed emission, has been detected, and that was a very important result because you can see here, MAGIC has also one optical pixel in the center and is able to detect also the optical emission from the pulsar, and you can see from the graph very nicely the pulsed emission and optical here down. Then at that point Fermi wasn't operating yet, so this is an old clock, but looks the same with Fermi. Then you see in the MEV and GeV gamma rays nicely the positions like Fermi, and then continue at higher energies nicely the MAGIC result, the same positions. The important thing is that there are very numerous fighting pulsar emission models for this gamma ray emission. The emission can come here from outer gap regions, can come very, very close from the neutron star here or here in slot gap regions. And you have to understand that for the highest energy gamma rays to escape, it must be further away from the pulsar because of the very intense magnetic field that would immediately induce pair creation from the highest energy gamma rays, and they would be absorbed, so they would be lost. So the conclusion is that these kind of polar cap models are excluded, and that the emission should come at least from several stellar radii away from the pulsar. What is also interesting is that in the case of the crab, the gamma ray pulsations and the radio and optical and everything is very well aligned. All these peaks are very well aligned. But in other cases, they are not completely aligned, and then it's possible to discover some pulsars in gamma rays that were not discovered in radio or in optical. So we have another possibility to discover new pulsars. And here you see very well how the MAGIC result connects them to these measurements by the satellite. And the point is that there is a very strong cutoff in the emission, as expected. And then beyond that, you see only the upper limits. So it is important that MAGIC, for instance, had this very low energy threshold, otherwise it wouldn't have detected this pulsar. And it's the only telescope so far that can do it worldwide, still. Coming from the crab to more of the sources in the galaxy, this is a galactic plane scan made by H.E.S.S, which is another array of 4 CHERENKOV telescopes. And they did something very nice. They have a larger field of view of 5 degrees, and they were scanning the Milky Way for in total now 2,300 hours, so they spent a lot of time on it. And this is actually now, as I learned, an old map, because in the Texas Symposium they showed the new one. which is even nicer, where you have even more features than in this one. So what you see is that really along the galactic plane there's one source after another, and they're really, really plentiful of sources, some even outliers a bit further away. And so it was a bit of a surprise, because before H.E.S.S there were only a handful of very high energy gamma ray emitters known, and they point to the galaxy and they see so many sources in the galaxy. And at the beginning, in fact, they were believing that this was fake. They didn't believe it at first, until then there was a cross-check from Magic, for instance, on a couple of sources, and we saw exactly the same. And so then finally now they are very well studied. And as you can see, they are so large, some of them several degrees even, that even with our limited resolution we can study morphology, like in this case, which is a very large supernova remnant, RxJ 1713, which is so huge, several degrees, that you can even see distinct features and see a very nice supernova shell. And what is interesting is that it correlates absolutely perfectly with the X-ray shell, if you correct for the different resolutions of the experiment. And this hints to the fact that this has the same particle population, and that in this case it's probably electrons that produce synchrotron, which you see in the X-rays, and then again with inverse Compton the gamma rays that you see in H.E.S.S. This one I think is 2 degrees even. It should be. It's cut here. Let me see. Yeah, it's this very big block there. Yeah, this one. So it's 1, let's say, a bit more than 1 degree. Yeah. Not only. Let me come to it. Because many of them are unidentified, in fact. Some of them are identified with supernova remnants. The identification is especially clear when you see this shell, which has happened, to my knowledge, so far only for 3 or 4 of them, because not all of them are so large. Many of them, surprisingly, are unidentified, and they all share some characteristics in the sense that the spectra are very, very flat. I mean, this is multiplied with E squared, and in E squared, in many cases, it's really completely flat. And all of them seem to extend up to 100 TeV, and there's no apparent cutoff visible. I mean, and here at this point, 100 TeV, as I told you, this is the energy range we can cover. So here we are limited by our experiment. We don't know what is happening beyond. So studies have been made trying to identify these objects. Here you see one of them, and here you see a map for the overlaid contours that has also X-ray sources and radio sources, and directly with this morphology, I mean here also this source is resolved, you see nothing that fits this source. So it is very surprising. During this year, Fermi was starting to discover more and more pulsars, and the prototype of these unidentified sources is called DV2032, was already discovered with older generation telescope long time ago. And finally Fermi found a pulsar inside of this object. So now we believe that this is actually a pulsar with nebula, similar to the crab, but simply the pulsar is not pointing directly towards us. So we didn't see the radio emission, but the angle of the beam from the pulse gamma ray component is slightly different, and we are able to see the gamma ray component, and of course then the extended gamma ray emission. It's however a bit surprising that we are not seeing the synchrotron emission from the electrons and the other wavebands. That's a bit surprising, but can depend on the age of this pulsar and the supernova remnant, because then you have different fluxes and so on. Leaving the galactic objects and coming to extragalactic objects. I showed this already last time, but maybe not everybody was there, and I wanted to quickly come back to it again. When we talk about extragalactic objects, usually we talk about AGN, which are active galactic nuclei, which means that you have a supermassive black hole in the center of these galaxies that are secreting matter with an accretion disk. You have an opaque torus of dust around it, and they are producing relativistic jets and shocks in these jets. So now, depending on from what angle we see this this AGN, we see these nice jets in the radio, or we see directly here inside, and then we call it a blazer because it's very bright when we look directly into the jet. So M87 is a nearby giant radio galaxy where we see these jets very nicely. I will show you in a minute. And it has a very large mass black hole, almost 10 to the 10 solar masses. And we can see that it is actively accreting matter and has these plasma jets. And we can constrain that the viewing angle should be something like 30 degrees, so we're not looking directly inside, we're looking from the side. It's 16 megaparsecs away. And since long time was believed to be a source of the highest energy cosmic rays, and fortunately finally was detected in very high energy gamma rays, because, as you know, from the cosmic rays, because of the charge and the deflection on the magnetic field, we cannot trace them back to M87, but with the gamma rays we can trace it back to M87. What I will show you also is that there are a lot of features, structures in this jet, and we did a long monitoring campaign with several instruments observing the variability, and found finally that the emission of the very high energy gamma rays is most likely coming from the core. So long explanation, here is finally the images. This is, in radio here you see, that is actually extremely extended. This is 20 kiloparsecs here, if you cannot see it. And you see the jet and the counterjet, and you see also that how it is interacting with the intercluster medium, and is bent, and is absorbed and diffused. And then what we can do is zoom in here, and you see in the X-rays these knots, so-called knots, bright structures in this jet. You see the same in the optical, and even you can correlate these individual knots from X-rays to optical. And also in radio you see these features. And radio gives us the best resolution. Here we can zoom into this even smaller region, and you see that somehow it never ends. We don't have enough resolution to see the black hole itself directly here. We still see the jet and we see a very bright nucleus, but the resolution we have is not sufficient. Actually here this is the resolution. This is a length scale in centimeters, and you see the angular resolution of the CHERENKOV telescopes is just good enough to see these lobes, so it would be something like this. And then you have the kiloparsec plasma jet, then here you have VLBA, which is 5-6 orders of magnitude better in resolution. But what we found was that the very high energy gamma ray emission is variable on the time scale of days. And then you have a very strong handle on the size of the emission region, and suddenly you are better even than the VLBA resolution, because you want that this emission region is causally connected to each other, and suddenly you're getting much closer to be competitive. And the virtual radius of this black hole is still an order of magnitude smaller than what we can achieve. So what did we see? We saw here, you see, before the campaign it was very steady and very low in flux. This is gamma rays. And then we intensified, we saw some feature here, then some very nice flaring activity here, going down again to much lower state and very quiet. Now the interesting point is that in the other wavebands, here this is X-rays, down is radio, you see that this one of these knots, so-called this HST1, was actually rather quiet and very stable, but also the other knots and the other parts of the jet were very quiet and stable. Only the nucleus showed some increased X-ray activity, and similarly later we saw from the nucleus, also in radio, that the emission is increasing. We expect that this radio emission is coming from diffused electrons, synchrotron emission from them, and we expect it to take more time for the electrons to travel and diffuse. And we see this increase later, but the rest of the jet with all these knots is still very stable. So the combination of this gamma ray flare with the other instruments that could resolve the jet was telling us that it must come from the core, and then the time scale of this flare told us it must be a very small region in the core of the black hole, and that was published in Science a year ago. Now, another thing that we can do is we can probe the transparency of the universe through gamma rays. If we see a very distant object, we can infer to the absorption in between. And this is now so-called, well, a quasar, which in the end is also an AGN. But this time, really, we are looking into the jet, not like H.E.S.S, where we're seeing it from the side. And 3279 is famous because it's very, very bright and also very variable. And so far, still, it is the most distant object that was detected at very high energy gamma rays. 2 times, once in February 2006 and once in January 2007. I was also working on this data. And what is interesting is that at this point, when these detections were made, the predictions for the transparency of the universe were quite pessimistic, let's say. We were expecting that there's a lot of infrared radiation from the early stars, from the early galaxies, from the early AGNs, in fact, themselves, that produce a lot of infrared radiation. And because of that, we were expecting that the universe will not be very transparent to gamma rays. And this would have meant that the spectrum is strongly absorbed and becomes very soft, but the emission was harder than we thought, so the conclusion is that the universe must be more transparent to gamma rays than expected. And this was possible with magic because we have such low energy threshold, and also we actually extend our duty cycle to observe during moon, which is not always possible for the other telescopes. But what we finally saw, these are the magic data here in red, is that it becomes very difficult to understand this emission. In case of this object, you expect to have 2 peaks. One is mainly, again, the synchrotron radiation, and here in Compton there is some debate. There can also be some protons in the jet, and there are some models also with protons and leptons. So there's a lot of debate how this shape is explained. But you see maybe also that we cover 16 orders of magnitude. This is very challenging because if you really want to understand and model this object, you need all of the data from all the different experiments. And as I said, the flare lasted, it's very rapidly flaring. In that case, the flare lasted only 1 day. So if you observe 1 day later with the X-ray or the radio, it's already a different story, and it's very difficult to make correlation studies here, especially since the CHERENKOV telescopes are pointed experiments. And also the data analysis typically lasts 1 day. So you realize 1 day later that you had the flare the other night, and then it starts to get too late. So here, when we were deabsorbing the spectrum with the extragalactic background light, we got a very rapidly increasing spectrum, which was very strange. And we were able to put constraints to the EBL, which are here shown in green. And, there are lots of measurements, but these measurements are very challenging because of the zodiacal light in our own solar system, produced in our own solar system. So many of them are actually measuring zodiacal light, and it's very difficult to subtract it. So lots of it are just upper limits or are coming from source counts, from Spitzer or something. So now, actually, a couple of years later, this was published 2008 in Science. A couple of years later, we have more data from source counts, more observations from galaxies. We can constrain this population of early stars better. So now the models are actually converging towards these lower limits that the observations from the TDV was already setting. So it is somehow converging, but in fact on this angle here, on this part, there are still the largest divergence, and maybe there can still be some work done. How short, how fast are these flares? I was talking about flux variability on the timescale of days, but that is not the record. The record is actually a timescale of minutes. Here we have one of these, again, blazars, where we're looking into the jet, Macarin 501. This object is quite close to us. I mean, in terms of redshift, it's of course hundreds of megaparsecs away. And you see here it was quite stable, and then it got into sunlight flare again here. And you see it here in different energy bands, starting from 150 to 250 GeV up until 1.2 to 10 GeV. The point is that we can see somehow that the peak of this flare is somewhat shifting with energy. I was drawing some lines here to make it maybe more visible. And then people were extremely excited because they were thinking that there may be some quantum gravity effects, in the sense that the highest energy gamma rays are maybe a little bit slower than the lower energy gamma rays, and we actually have Lorentz invariance and variance violation. And well, there were some discussions on that, but the big problem is, of course, also that in principle one can imagine the source itself needs most likely time to accelerate particles, to bring them to the ultra-relativistic speeds. And these highest energy gamma rays, in whatever model you are using, will come from the most energetic particles. So it can also be seen in such a way that these 2 minutes or whatever difference is the time that you needed to accelerate the particles, and that is actually an intrinsic effect. So personally, I actually favor the intrinsic effect because it would tell us a lot about the source. It would tell us a lot about what is happening there. But also one has to be careful because in principle it's not so statistically significant. I mean, here in this plot it looks quite nice, but it's actually on the resolution of the binning that we had on the point, so it's also not exactly significant. Not only ATNs are sources for very high energy gamma ray radiation. Recently the starburst galaxies became a very hot topic. This is M82 seen by the Hubble Space Telescope. You see these well, very nice particle rings that in this time are not produced by the supermassive black hole in the center, but are coming from very very strong stellar winds from very young, very massive stars and star formation regions. So again, for us, this is very well. From the sky map, it's just a single point, so it's not really a result at all. But the interesting thing is that from the spectrum, from the measurements, it is consistent with what we expect from the inverse Compton radiation, from branch Starlong. Well, branch Starlong in our energy range is almost insignificant, and some by zero decay. So the model predictions for this starburst galaxy were already quite good. I mean, it is, let's say, within what we are able at the moment to measure. So we cannot really improve on it. Another example is NGC 253, is a starburst galaxy visible from the south. And what I would like to note here is that for the first time we were actually able to resolve something is maybe said too much, but these contours are from the optical. So this is the extent of the galaxy, and this is the extent of the very high energy gamma ray emission, and you can see that it's coming from the core. So at least we were able to constrain where the emission is coming from. It's not coming from the outer edges of the galaxy, it's coming from the center. And we know from the optical observations that the starburst regions are here. So this is another strong confirmation. And in that case, the emission was actually a little bit lower than what was predicted. Well, there are different models, and they more or less are still acceptable. Last time I already talked about these new Fermi-detected gamma ray bubbles. I found a better image now that is maybe easier to see them here. And in fact, if you now think of M82, you will realize that it's not entirely so different from what we saw with M82. But of course, on M82 it was on a much larger scale. And some people believe now that our own galaxy was in a very strong starburst phase in the past and produced these winds that are now still visible in gamma rays. Yeah, and what we can do with all of this, we can check how the star formation rate, for instance, correlates with the luminosity that we measure in gamma rays. And you see that there's a very, very nice correlation. Now this can be very interesting in the future to predict, for instance, for some other objects, the luminosity, or if we detect something, we can infer on this back to the star formation rate these objects. That is very nice. By the way, also the Andromeda galaxy has recently been detected in gamma rays, and it's also on this correlation. Now I already mentioned these are the magic telescopes on Alzheimer. I just wanted to show them to you so that you also see them in case you haven't been there yet. What is nice to note is that since fall 2009 the second telescope is working well, and everything is really as we expected. In fact, it's even better than what we were hoping for. So we have very significant improvements in the angular resolution, the energy resolution, and in the background suppression. Especially the background suppression is very important for us. And well, I don't know, I think I still have some time. We already have a lot of new results, and we were announcing them in astronomer telegrams, because it typically takes time until the papers are published and you want some follow-up in other wavelengths. I showed you how important it is to have also other wavelengths. So there was, for instance, the discovery of another radio galaxy, IC310. This is interesting because this radio galaxy is in the Perseus cluster, and it's one of those head-tail radio galaxies that strongly interacts with the intercluster medium, where the jets are actually bent very strongly because of interaction with the intercluster medium. And another case, and actually Josefa Becerra here from the IC was working on that, was a strong flare from PKS 1222. This object is interesting because it's relatively distant for us, redshift 0.4, so only a little bit closer than 3C279, and it was flaring so rapidly that we detected it in only half an hour of observation, and even on smaller timescales we found variability. And again, this constrains the emission region very much, and we can be here much more sensitive than other experiments because it's so distant you cannot even with VRDA resolve this jet. So we are much more competitive here when it comes to the emission region size. Another result, this is actually based on my work here done at the IAC, was that also in Fermi we have sources which are unidentified, where we don't have the counterparts yet. And from one of them we discovered then very high energy gamma ray emission with magic, and then also variability, which correlated also with X-rays, and then we were able to trace these previously unidentified source to an H.E.S.S, to one of the blazars, which are also pointing directly to us, which was so far not yet clearly identified as such. Another discovery made in October was another H.E.S., which is actually in that case, let's say, state-of-the-art H.E.S. is not too distant. It's one out of many. This is actually maybe more interesting. The central galaxy of the Perseus cluster, NGC 1275, was also finally detected by magic. And this is a very, very interesting galaxy because it is very complex in the sense that it had a lot of merging activity in the past. It has a lot of interesting filaments, and it's very interesting to study this object. What does the future hold? Well, we are trying to improve as always, and here, for instance, the H.E.S.S collaboration is trying to build a very, very big telescope, 28 meters instead of the 17 that Magic is having. But they have a lot of problems with that. Number one is that steel got very expensive and they paid a lot of money for it, and number two, that also the company was not constructing it really as they wanted, and they had problems when they were trying to build it up. So now everything shifted very much to probably 2012 or so. And what I also wanted to show you is that here this is an old plot from the ICRC in 2007 was this conference, I think, where you see how the number counts of sources in X-rays and gamma rays and very high energy gamma rays have increased over the years, and you see that we have a very nice exponential increase, all of them. And now with the Fermi satellite, this nicely continued up to 1,500 sources. There was a long gap in time because there was no satellite here. And for us also, we are still on track for this increase, but there were continuously telescopes, so we have more points. So, this is my summary. The field is rapidly growing. We have a very large variety of sources, and they continue to surprise us all the time. We always discover something more. Crab Nebula was discovered 20 years ago, and now we find this variability, which is very surprising. In general, variability is the key word for this field because it is apparently happening in almost all the sources except for the supernova remnants. And lots of these unidentified sources are starting to be revealed now what they really are. Some of them pulsars, others H.E.S. We need these multi-wavelength studies. We need to work together with lots of other telescopes, and we can constrain very strongly the region and size of the emission region, the extragalactic background light, and maybe even new physics. We are on the verge of doing that, and maybe soon also the extragalactic magnetic fields. And the future is bright. We are working to build another even larger array, but we are going to have a talk about that by Irene, hopefully in February. Thank you.
The correlation you showed between star formation and gamma ray luminosity.
This one.
Yeah. If you include AGN, where are they?
Well,
first question: how do you measure the star formation with H alpha luminosity?
Okay. This is a good question. I have to check how they did it in the Fermi paper. I took this actually from a Fermi paper that was published a few days ago. I'm guessing, yes, that they do it in that way. Yeah. But for the AGNs, actually, it's a good question. If we really want to do it for an AGN, we are strongly dominated by the jet. It's very bright. So we would have to subtract somehow the luminosity from the jet. And it's not yet fully, let's say, precisely modeled. I mean, the free parameters and the model is very large, so the uncertainties are very extreme. And the star formation luminosity that you get from the star formation is much, much lower. So it's only a very small contribution to the signal we are seeing. So for the ATNs, I would say at the moment it's too difficult. We cannot do it yet. But for the galaxies which don't have a very active supermassive black hole, then of course we can do something. So it's depending very strongly on the galaxy.
Indicates that the gamma rays are produced in the star-forming regions?
Yes.
Who produces the
Well, actually not the stellar winds themselves, but there's of course then also a correlation with the supernova explosion numbers that you have, and it's the supernova explosions that are supposed to produce them. And recently also a paper appeared that suggested that the pulsars that are produced in those with their pulsar winds, like the Crab Nebula, also have enough power to fuel the gamma ray emission that we're seeing there. So, yeah, these two components, the supernova remnants and the pulsars.
How bright is the flash that you are measuring compared with the background of the sky?
Well, compared to the background in the sky in these short nanosecond time scales, it's much brighter, up to 1,000 times brighter. It depends very strongly on the energy, of course. I'm talking now about an energetic event. We are limited at this 25 GeV, 50 GeV limit is because at some point these flashes become comparable to the NSP. Yeah.
If our eyes were fast enough, we will see it.
Yeah. Actually, the pioneers of the field, one of them was once claiming that he can see it.
Very fast.
Yeah, but the brightest one.
Any more questions, comments? So for the quasar spectrum that you were talking about, the EBL constraints.
Which one?
Yeah.
This one?
No, the previous one, I think.
one.
Yeah, this one. Is that when flaring?
Yeah.
So when it's not flaring, can we see anything or not?
No, we cannot see anything. Actually, it's not so surprising. You see here in the satellite range, this is during one of the flares, and it connects quite nicely to our measurement. And this blue one is during a quiescent state, and you see how rapidly it is dropping. We would not see anything from that. It's going down fast.
Thank you.
In your H.E.S.S plot of the galactic plane, the search, why don't you see magnetars and black electric arrays?
Okay, we do. Well, as I said in some examples, it's not always clear which one is identification, but there are some objects where the H.E.S.S people claim, or where it's possible, let's say, that they are associated with magnetars. And there are indeed binaries detected, like in case of Magic LSI plus 61, I didn't mention this one now, or in the case of S, LS 5039, where you see in gamma rays the period in the signal going up and down, and you can clearly say that this is this binary. But so far the black hole binaries, the ones where we are really sure that there are black holes in the system, because for these two that I mentioned, we are not sure. The black hole binaries, we didn't see them yet. They were actually quite strict upper limits for magic for Cygnus X3 recently. It has been seen by Fermi, and they saw also the periodicity during a flare correctly. But it seems that there's strong absorption for the TeV gamma rays in these systems, which is not so difficult to this, because there's not the photon fields around.
One more question.
Maybe I should understand this, but how do the gamma ray bursters fit into this whole picture?
The gamma ray burst? Yeah, well, so far no gamma ray burst has been detected from the ground. It's an additional talk. Maybe I can do part 3, gamma ray burst. They have not been detected from ground. Magic is trying very extensively because we are able to position the telescopes very quickly in 20 seconds by 180 degrees around. But, well, we get the alert from the satellite, it needs to travel to us, and something like 30 seconds delay is typical. And the best chances are in the prompt phase so far. I mean, there's also extended cooler phase and afterwards, but the flux is too weak for us to do that. We need the prompt emission. We need to be lucky to really be fast enough and have one, which is also close enough to us, because if you're beyond this gamma ray horizon with the EBL, then it's also too much absorbed. You need the lowest possible threshold of 25 GeV, and then many people are waiting for that actually to happen, because Fermi detects only one photon of a GeV at 30, one photon of a gamma ray burst at around 30 GeV, whereas Magic would be able to detect thousands theoretically. So the statistics would be tremendous. Yeah.
Thanks.
Karsten, one more time for next.